Hello, this is a video for COMP345. This is week 10, slide set 9. There's going to be only one video for this slide set. This is about operator overloading. So let's go to the slides. So we already saw some operator overloading before, so that we can somehow incorporate that in the project. So we presented some of them before. Here I'm going to go and do a more in-depth description of what they are and their particularities. Move this here. Okay. So a very typical example of operator overloading is you declaring a rational class. You may have already seen this example before. So the idea of a rational class, you have a numerator and a denominator. And here you have your constructor, default constructor, and your copy constructor. So what you want to do is define these numbers and being able to, do some arithmetic operations on them. So we may actually implement these operators as you would do in Java. You might want to add this add operator inside of your rational class as a, as a method of the class, not an operator. So this is not an operator here, it's just a standard method. So in this case, you would have a add method added to the rational class that takes another object of type rational, and it basically adds the current rational number with this one that is provided here as a parameter. So here you have the formula that basically is using the denominator of the parameter and then adding it with the denominator of the current object and then multiplying it with the numerator of the parameter rational number. So that this is both using a parameter as well as the current object. So you will have the same thing happening if you implement, you could implement your operators as members of the class. We shall see much later in this lecture that it's better to actually implement them as free operators for various reasons that we'll see later. Now, the point with which is not so nice about this add operator is that let's say you want to add three, you want to define three different rational numbers, A, B, and C, and then you want to do A plus B plus C. So if you want to use this method here, then you would have to go A dot add B dot add C. It's not very elegant. So what you may want to be doing is to say D is equal to A plus B plus C. Now, that may seem to be a wild wish if you come from Java, yes, but in C++, because C++ allows you to overload your operators, such as plus, then you're actually allowed to do that. The language enables you to be able to do that. Now, how would you define such an operator? Because here, essentially, what you're doing is you're defining somehow a function whose name is plus, which is used with some kind of infix notation, basically. Okay, so you are defining the plus operator. So in this case, that's the syntax you are using to declare an operator or define an operator. You go operator and then the name of the operator, and that's basically the name of a function that you're defining, except that it's a particular kind of function. It's an operator. So operator is essentially a keyword. As we will see later, you're not allowed to define any kind of operator. There's a fixed number of operators that you can define, plus being one of them. So here we're overloading the plus operator that is actually a member of the class rational. And this plus operator a plus operator by definition is a binary operator, so it needs two operands. In this case, the left operand is the object, the current object itself, and then the right operand would be another object that you pass as a parameter to the plus operator. So basically, it's the same body as you would have had for, as I shown earlier, for the add operation, except that here it's the plus operator. Okay. So there's no difference really in terms of how you define an operator and how you define a function or a member function. It's just that you use the keyword operator here and the name of the operator you want to overload. So you're allowed to actually, well, the great advantage of this is that you can now you can define your own types, and now you can overload for example, the arithmetic operators as we just saw here. So that allows you to use your own types in mathematical expressions that, for example, imply or use arithmetic operations. But there are limitations to operator overloading, very important to understand them. So at least one of the operands must be of a user-defined type. So you could not, for example, define an operator that the plus operator for two ints, for example, because that you can't overload the operator for the int type, which is not a class. Okay. So there has to be one of those that is actually a user-defined type or a class type that you have, that you're defining in your own code. So that's also, as I mentioned, as I hinted at before, this is restricted to a fixed set of operators. I'll show what they are later on. You will see that there's actually quite a number of operators you can overload. Some of them are very obscure. I'm going to give you some examples toward the end, but the vast majority of operators you implement would be, for example, the increment operator or the arithmetic operators or the square bracket operator. I'm not going to give an example later on that. And also the precedence and the associativity of these operators, you cannot change them. This is hard-coded in the compiler. Okay. So you cannot change the priority in an expression of the operator that you are overloading. Okay. The operator itself, its associativity and precedence is hard-coded in the code generator of your compiler. So that these are limitations, these are things you cannot do, but here are things that you should try to not do. For example, you should not, like if you overload the operator plus for your class, it's advisable that you actually make this plus operator do something that is related to the notion of addition. Okay. For example, for numbers, it's quite straightforward, but for example, you might remember in Java, you could actually use the plus operator on strings, which basically means concatenation. Okay. So sometimes this can be a little bit different if you implement it for different types, for example, such as strings. But try to make sure that when you overload an operator, that people are not misled by what is the operator name versus what it actually is doing. Okay, nothing will prevent you from, for example, implementing an operator plus that does multiplication. You can write whatever code you want, but it would actually make the use of your operator misleading to your fellow programmers that are using your code or reading your code. So this is the complete list of operators that can be overloaded. So you see you have the arithmetic operators, you have the logic operators, you have the comparison operators or relational operators. You have the increment operators, you have the stream insertion and extraction operators. You even have more obscure ones, which you might wonder. For example, you may also, or the square bracket notation is an operator. Even the open close parenthesis is an operator. Even new and delete are operators that you can overload. I'm going to give an example of the square brackets and the new and delete at the end of this slide set. So in the example I gave earlier, these operators were actually, or the plus operator was implemented as a member of the actual class on which you want to add this operation for. So here, essentially, you are providing the minus operator as a member operator of the rational class. Okay. But see, this is here for a unary operator, because you have unary operators, you have binary operators, you have one ternary operator, but you're not allowed to overload it in C++. So this is for essentially the unary minus. Okay. Unary minus is basically changing the sign. If that would be a number, if you do -4, it's basically applying the minus operation on 4, making it -4. So it has only one parameter. So if you would implement it as a member of the class rational, let's say you want to implement a unary minus operator for the rational class, you would declare it as such here. This operator minus is a member of rational, does not have a parameter. So that's the unary minus that we're talking about here. Here you are actually declaring as a free operator. So you see that preceding here operator minus, contrary to what we had here, this operator is not part of any class. So it's basically declared in the global scope, and it applies to an object of type rational. So you see that this is a unary free operator for the rational class. So you see that the code is mostly the same, except that here it takes effect on the current object so that it would use the current object's numerator and denominator to apply the minus operation. However, here it would actually take effect on the object that is passed to this operator. So you can declare your operators. If you declare operators for your own classes, you can define them or declare them as members of your class or as free operators that operate on an object of your class type. We'll see that later on that there are some advantages and drawbacks of each of these. Then that was it for unary operators. If you implement binary operators, then basically binary operators such as plus has a left operand and a right operand. If you define it or declare it inside of your rational class, then the left operand would be the current object. And then the right operand would be the object that is received as a parameter, as the single parameter of your plus operator. So then you would refer to the left operand using this, and then you would refer to the right operand using the parameter name here. If you would like to implement your operator as a free operator, then it's not residing inside of an object anymore, so it cannot use the current object. So it needs to have both the left and right operands of the plus. Then, of course, in the code here, you refer to either left operand or the right operand rational number. So you see, you can still here implement them either as member operators or as free operators. Um, so there are some things that you could add. You don't have to, but it's nice to add them. Or there's very often some conventions that people use or rely on. Namely, when you are passing parameters to an operator, if you want to somehow optimize the code that you are that it generates, it's nice to actually pass your parameters as reference so that you don't have copies of objects that are passed to your parameters, so that you basically save memory as you're passing these objects as parameters. If you pass them by reference, a copy is not made. However, the objects that are passed to these operators, such as the plus operator, they should not change the values of the parameters that they receive. So generally what you do is you define or declare your parameters as constant reference, so as to make sure that you don't make a copy as you pass, and that as you pass the reference, that you actually cannot change the value of the object that has been passed. And then what you may want to do also is to declare the return object of the operator as a constant. So that the result, for example, of your plus operation is not an object that you can actually change. We'll see an example of that, well, actually here. So if you would not have const here, you could actually write something like this, okay? So here you basically have this object R3, and then you assign R3 to the result of R1 plus R2. So if you would not have const here, well, believe it or not, that would actually be valid, because R1 plus R2 is actually an object. And here you're assigning a value to an object. However, if you declare the result of R1 plus R2 as const, you cannot change the values inside of the object rational. So thus you cannot call the assignment operator. You cannot use a result of a plus operation, which returns a const, as the left operand of the equal or assign operator. Okay. So declaring this as const here actually prevents that you are able to do something like this here. So here we go with the increment operator. This is very often something you would want to overload. So how do you go and do it? So as you may know, there's a pre-increment and a post-increment operator. So how do you make a difference between the two? So if you want to do the prefix increment operator, or for example, plus plus C or plus plus V, then that's how you declare it. So that's the operator plus plus, that is a member of your rational class. And it's basically implementing, incrementing this rational number um, by one unit. And then you actually return the object itself, okay? Because the plus plus operator has two effects. It actually increments the value and returns the resulting incremented value. However, if you want to implement a post-increment operator, which is actually returning the value, then incrementing the value, then you would have to actually create a copy of the object, incrementing the object itself, and then you actually return the initial value. Okay, so here you do those things in a different order, as you may see from this one here. Here you actually return the original value, then you actually increment it. How do you make a difference between these two? Essentially here, C++ uses this dummy int parameter here. Okay, so you in, to express that this is the postfix increment operator, you need to have int here. This parameter is not used. I know it's weird, but this is how you do it. Okay. And that's one of those that we saw very early in the course because we asked you to implement that in your project. That's for overloading the stream insertion and stream extraction operators. So one of the things that's important to understand about the stream insertion operator as it's used here in this example is that you can have, a series of stream insertions inside of that inserts in the same stream. Okay. So if you want to be able to do that, then you have to basically the operator has to return a reference to the initial stream so that the subsequent objects are actually adding to the same stream. Okay. So the stream insertion operator is going to insert something in the stream and then returning the stream itself so that another one that is potentially in sequence can add to the same stream. So you see that particularity, or how you achieve that is that you actually pass the stream as a reference, enabling you to change the stream. See that here it's not a const stream because you're really adding to the stream. Okay. If you would put const here, you would not be allowed to add to the stream or to use the stream insertion operator here to add something to the stream, which should not be const. So it receives the stream as a reference. It changes the stream by adding to the stream, and then actually returns a reference to this stream so that later on another stream insertion operator can take this resulting stream and then add to it again and again. Okay. So you need to, in order to do that, you need to pass the stream as a reference, use it here and change it, and then return a reference to the stream. Of course, here one thing that is potentially confusing is that you are using the stream insertion operator inside of the declaration or definition of your stream insertion operator. Here, of course, this is a stream insertion operator for an int. Here, this is a stream insertion operator for a char, and this is for an int again. Okay, so here it's a different overloaded version of the stream insertion operator that you use in your that you use inside of your definition of your own stream insertion operator. Then, of course, if you want to do the stream extraction operator, it's very, very similar. So you use iStream instead of OStream, and you essentially extract from this input stream. Very typically, you would do that with cin, but that, as we saw earlier for files, you could also implement that or use that for files to extract values from files. Okay, so here we go into some maybe more obscure kind of operators that you can overload. You can actually overload the casting operators. So you might recall that you actually can do something like this in C style. You can actually go take this B here, that is an object of type rational, and then apply to it this casting operator, basically saying that you want to cast B into a float. So in order for this to work, then that would mean that you have this operator here that you have overloaded. Okay, so that's floating point operator that you have overloaded here. Its behavior is that it returns division, the double division between numerator and denominator. So you see that here, if you do something like this, you define your rational B, and then you say you want to put this B into a float F, then this operator here would actually be implicitly be called to initialize this value. If you remember, we talked about this notion of conversion sequence when we talked about initialization of variables in C++. This is actually exactly what's happening here. So this is essentially an operator that can be used in a conversion sequence. Okay. I remind you that what can be used in a conversion sequence by the compiler is either a constructor of your class that receives an object of a certain type, which is different from the type of the class itself, or a casting operator like this, which can also be used in a conversion sequence. So here there's a conversion sequence that is used implicitly by the compiler for converting this object B into a float. Okay. Here you actually triggering some kind of conversion sequence also, but explicitly. Here it's actually implicitly that the compiler would decide to do that. In this example here, you see that I have a series of values that are being output. It seems that this would actually be executed last year. However, you may see that that's an example about the precedence of operators, as I hinted at before. Fact of the matter is that a casting operator has extremely high precedence. So if a casting operator is involved in an expression, then it would actually be, one of the things that is executed first in the evaluation of the entire expression. Here you have this casting operator that is applied on B, and in fact, it has higher precedence than any of the other operators involved, including this one, this one, this one, this one, this one, this one, and this one. So in fact, float would actually, the float conversion or casting operator would be applied first. So that's why as you print out the result of the printout of this statement here would actually be such as this one here. So even though here it appears that you would print out B after having incremented it, and then you would actually transfer this this incremented B into a float. No, that's not what happened. So in fact, the value of this was calculated before. So it's actually the conversion of the initial value of B, which is transferred into a float. Then this is applied, and then all of the stream insertion operators are applied. So you see that this, because this here has very high priority or precedence, it has, if you're not aware of the precedence of your operators, can be misleading. And there's no way you can actually change the precedence of your operators. This is something that is hard-coded in the code generator of the compiler. Okay, so let's go to the assignment operator. Again, we saw how to do an assignment operator earlier in the course. Here I'm going to go a little bit deeper into how you should do it correctly so that it works in all cases. Okay. So here you actually implement your assignment operator. And this is a member of the rational class, and it takes as, so that's your left operand is what is the rational object that is to the left of the equal or assignment operator, and the parameter here is the right operand of your assignment operator. So essentially what you want to do here is to actually take the values of the rational number that is to the right of the equal and then put them in the current objects, numerator and denominator. And then eventually you return the object itself. Okay. Well, that may seem to be reasonable. That seems that this is what you want to do. However, one of the things that is important is that one of the things you want is to be able to say, for example, A is equal to B is equal to C is equal to D. So that if you want to have a cascade of assignment operators, you should actually return the result as a reference, exactly for the same, using the same reasoning as I explained for the stream insertion and extraction operators. If you want to define an operator for which you can have a cascade of operations with it, then you have to define it as to return a reference. As we saw earlier, if you don't define your assignment operator for your class, there will be a default one that's going to be provided by the compiler. So what it's going to do is do a member-wise copy of all the members, but it's going to be a shallow copy. As we saw earlier, if you have some members of your classes of your class or objects which are pointers, then all it's going to do, the default one, is only going to copy the pointer values and it's not going to make a copy of what these pointers are pointing to. So if you want to have a deep copy of your assignment operator, you must implement it by hand. Okay. Now, what if, let's imagine, let's go in this direction, and let's imagine, because in this current version of the rational class, the numerator and denominator were not pointers. Okay, so let's add to this, or let's change this class and assume that numerator and denominator are now pointers to an int. Okay. Then let's see what happens if you're trying to define your assignment operator. So what you might want to do if you say, okay, I'm going to implement a deep copy or an assignment operator that implements a deep copy, because now my numerator and denominator are pointers. So I'm going to copy the values pointed to by the pointers of the original object. I'm going to create a copy of them on the heap, and then I'm going to create new object whose two pointers are going to point to the new copies. Now, if you might think, well, this is what we want to do. However, the thing is that if you do that, these two pointers, numerator and denominator, they used to point to some values that were allocated on the heap. Now what you say is, I'm going to make two copies of these, and then I'm going to make my pointers point to the copies. Now, and then I'm going to return this object, which has these new pointers to these newly allocated values. Now, when you actually return, what's happening here is that you've just lost the pointers to the original objects. Okay, so essentially you have a memory leak in your assignment operator. Okay, so that's not the right way to do it if you want to do a deep copy. So what you want to do is to actually delete what is pointed to by numerator and denominator before you actually create the copies and then assign them. Okay. It may seem that this is what you want to do to avoid to have a memory leak. But then let's imagine that you are, for some reason, going to write something like this. So that's basically called a self-assignment. You might say, well, why in the hell would I be doing this? Well, you're allowed to do this. There's no reason why this is not allowed. You're basically taking an object and assigning it to itself. Okay. Now, if you do that, looking at the code that you just wrote here, then what you do is you first free or delete the numerator and denominator, or the values that are pointed to by numerator and denominator, and then you want to make a copy of them. You can't make a copy of them because you've just deleted them. Okay. So when you're going to want to assign to do the assignment after deleting, they are not there, so you cannot make a copy of them. So in order to avoid this problem, which is not something you can prevent, then you have to do what is called a self-assignment check inside of your assignment operator. So if the right operand of your assignment operator is not the same as the left operand of your operator, then you do this. If not, then you just basically return the initial object itself. Okay. So anytime you want to implement a assignment operator that does a deep copy, it should have all these characteristics. It should avoid to do a memory leak by deleting the objects that were in the object that is to be assigned by the operator, thus avoiding the memory leak. Then you should make the copy, and it should only do this if both of the left and right operand are not the same. Now let's go into other details. Now, what if, for example, I have my rational plus operator, which at this point, as we define it up to now, the plus operator applies to two objects of type rational. Okay. Now, what if I want to have a plus operator that applies to an int as well as a rational object? For example, what if I declare my object A, which is 5/6, and then I want to add 25 to this rational object. Now I might say, oh, I'm going to overload the plus operator so that it actually takes an integer. So I will actually overload in my rational class the operator so that its left operand is an int. Okay. Then that does not entirely solve the problem, because what if I want to say, well, the plus operator is commutative, so I should be able to say 25 plus A. May seem very logical. However, what's happening here, if you define your operator plus as part of your class rational, whereas the left operand is in this case the rational object, and this one is actually the int that you want to add to your rational object. And then here the left operand is a rational type. That's fine, because that's the current object that you are adding to this 25 here. So your left operand is the current object. However, if you're trying to do this here, and then you would say, I would implement it as a member of the class, then in this case, the left operand of your plus is an int. So that would basically require that you overload the plus operator in the int type, okay, which you cannot do. You cannot overload operators on the basic types, okay. So essentially, if you are implementing your plus operators or overloading your plus operators as members of the class, you would not be able to achieve that here. You would be able to have this, but not that, which is not very elegant, of course. So this points to say, if you want to be able to do something like this, as well as something like this, you need to have your operators as free operators, in which case they are not part of any class, and you would not have this particular problem happening here. So if you want to have, for example, your plus operator on on two rational objects, left operand is rational, right operand is rational, this is how you would do it. If you want to have left operand is rational, right operand is an int, that's the operator you need. If you want to have left operand is an int and right operand is rational, then that's how you would do it. So you see that you need to overload the three different possibilities. Okay. And that's, again, I repeat, that would not be possible. This one here would not be possible if you would have the operator plus defined as a member of the rational class, because the left operand would be an int. So you cannot overload the operator on the int, the plus operator on the int type. So if you want to have something like this, you must have your operators defined as free operators. Now, one of the things, if you remember in the beginning of this rational example, my numerator and denominator would actually be declared as public. As you may see here, it's very convenient because here I was accessing the numerator and denominator members of the parameter, like this here, A and B. I'm accessing numerator and denominator, and this is a free function. It's not a member function. So for this to work, these numerator and denominator need to be public members. Okay. Now, maybe you see me coming. Yes, well, the solution to that is, of course, to declare these free operators as friends of the class if the members are declared as private. So eventually what you're going to end up having is, yes, this rational class where your members are private, numerator and denominator are private, and then you declare these three operators that we have defined earlier as friends of this class. Thus, they can access numerator and denominator. This is right here by far the most, I would say, orderly and widespread use of friend. When you declare operators, you declare them as free operators and you make them friends of the class on which they operate on. Okay. For all the same the reasoning that I've explained leading to this example here. So you have three ways of defining your operators. You can declare them as members. It has clear disadvantages as we saw earlier. I'm going to let you distill this whole thing here and go back to the reasoning that we had before as an exercise. So you can declare them as members. It has some disadvantages. You can declare them as free operators that are not friends. Of course, it has some disadvantages because it cannot access the private members. Then the optimal solution, which you see most often, is to declare your operators as free operators that are friends to the class on which they operate. Here are two last examples on some more sometimes useful, but sometimes also esoteric kind of examples. Here it is actually providing the implementation of the square bracket notation. Okay, the square bracket is actually an operator. So most often you would see, of course, square brackets used in conjunction with the notion of an array or a container of some sort, an indexable container. So that's basically how we're going to use it here. So you see that my class is called array. It contains a pointer to an int that is, of course, going to be a static array that it actually points to. And conveniently, it also contains the size. This is very similar to what you would see if you would look inside the code of the array class, the standard array class of C++. Which would need to be a template as we see later, but nevertheless, this is a similar idea. Then, as you see here, I have my constructor that receives such an array, and as well as the size of the array, and it's basically copying an array that has been declared externally, such as here, passed to my constructor here along with the size, and then basically it puts this array here inside of my object, and then puts the size 4 inside of my object. Then I can actually use the square bracket notation on this object here because it is actually overloaded on my type here. What does it do is receives a parameter, which is the parameter you have inside the square brackets here. And then essentially it returns the, for example, if you say R1 of 2, it returns the third element of the array that is contained inside the array of int that is contained inside of my object of type array. By, of course, using the square bracket notation that is somehow overloaded on static arrays, which is done internally or is hard-coded in the compiler, because of course this is not a class. Okay. Yeah, okay. So here you see that what this can enable you is to do some boundary checking. So you can check here if the index that you pass is greater or equal than the size. If it is, then you basically exit. One more nice thing that you may want to do is to, of course, throw an exception, which we will see later. Okay, so that's how you implement the square bracket notation on an actual class. Okay. Here is another example of things that you can also overload, because new and delete are two operators that you can overload. So you could declare your own class here named test, that actually contains an integer value. Extremely simple. And here you see that I have instrumented my code here so that when the constructor is called, it would actually output it to the screen as well as the destructor. However, I'm also overloading the new and delete operator. So you see here, this is implementation of my new operator for my class test. What it does is actually uses malloc. Malloc is a C function that is used to allocate memory. In fact, if you would see inside of what's happening when you call new for a certain class, it is actually eventually calling malloc. Okay. Malloc is the core function that you would use to reserve memory on the heap and then return a pointer to it. So here you're doing this by hand, you're calling malloc. The size here is the size of the class in question. So when you call, for example, here new test 5, then what is passed as a parameter of this here is this object test 5. Then there's a conversion sequence here that is applied between this and size t. Size underscore t is a special kind of type that is used to represent the size of a certain type. Okay. Then the compiler would know that it needs to determine the size of an object of this type and return this as an integer. Some kind of integer, because size underscore t is some kind of integer. So that when you call malloc here, that it actually reserves memory corresponding to the size of this object here, and then returns a pointer to it, which you assign to this pointer, this void pointer here. And then here, I'll put something to the screen, to the console, in my trace here, as we will see later. And then I return this actual pointer here. So here you see that what my new operator does is just basically goes and reserves memory that corresponds to the size of the object that I'm actually now creating using the new operator. Well, if you remember, or if you took some course that or learned it by yourself that that taught you about C, there's the corresponding function for malloc. When you allocate some memory, there should be a free somewhere that's going to deallocate this memory, or else you would have a memory leak. Okay, so malloc and free is the C brother and sister of new and delete in C++, as you see here. So what is that? What does it do when you call delete? It actually delete is acting upon a certain pointer, and what it does is basically calling free on this pointer. Okay, so free is the function, the core function that is used to deallocate the memory from the heap. So you see that your new and delete operators are in fact some kind of layer that you put on respectively malloc and free. And this is here an example of how you would overload the new and delete operators, so that if you execute this code here, as you may see, here I'm calling new. And then I'm creating this object and then calling, or I'm calling new to actually create this object. When I call new, what it does is basically it reserves memory for this object. And then after the new operator has been successfully called to allocate memory to this object, then the constructor is being called. Okay, because of course the constructor, one of the things that it may want to do is to put some values inside of this object. If this object has not been allocated yet, then it's going to try to allocate to put some values into something that does not exist yet. So the objective, the effect, the expected effect of new is to allocate some memory so that later on the constructor can actually put some values in these things, in this memory space that has been allocated to the object. So you see that in sequence here, you're calling new, and then that actually calls the constructor. So new operator reserves the memory for this, then the constructor is taking effect. That will eventually put 5 inside of the X member of the object, which we allocated space for using new. Then, of course, when I'm calling delete here, the inverse is happening. Okay, so first of all, I'm going to call the destructor. The objective of the destructor would be to free some of the resources that are allocated to this object. And then eventually delete is deleting the object itself. Okay. If you would be freeing the object and then trying to call the destructor, then this object would not exist anymore. So there's nothing you could do about it. There's no effect that the destructor could actually have. So you have to call the destructor so that it deallocate some resources that might have been taken by some of the members of this object and free these resources. And then you actually call delete to free the memory space allocated to the object itself. Okay. So that's about it for that lecture. See you around.